on in, everyone. Any questions while we're waiting for your fellow classmates? Hope you all had a great Thanksgiving. And if you don't celebrate that, I hope you had a good holiday.
I think I have a question about our upcoming MyLab mastering due dates, because what it's showing in Canvas is different than what it's showing in the mastering website.
Okay, the mastering website should have the right ones. It's basically a pain. If I decide to give y'all extension in the mastering website, then it's a real pain to go back and change it in the other one. So just whenever you're faced with that, just go ahead and assume the mastering website's correct, unless it's like worse. If it's worse, call me and or text me or whatever, and I'll fix it. But I know I went in Wednesday and changed all the due dates to make sense with what we're doing, so that all the dates in the mastering should be correct now.
Okay, what I'm seeing in mastering is that we have the chapter 15 homework due today, but then everything after chapter 15 homework is due December 15th.
Yeah, because December 15th is basically 2 days for the last day of class. So it's beyond what we're supposed to do our exam day. I think our exam day is supposed to be the 13th or 14th. And then that just gives you a couple days after the exam to make sure you finish up any last minute homework. I try to keep everything, I want you to do it before, obviously, so you can get a better estimate of what your score is and all that good stuff. But okay.
Yep, thank you.
Good question. Sorry about the confusion with the multiple dates and all that stuff. I used to not put dates on the ones on Blackboard or on Canvas at all, but students were complaining that they didn't get reminders, so I started putting dates on it, and then that became a pain, because when I change it, I gotta go to 3 different sites. I don't know. One day I'm gonna be a good teacher and I'm gonna have one class that runs smoothly. Today ain't that day, evidently. Anybody else have anything? So I had a real screw up this morning, and my poor students, I got 20 minutes in and I got deathly ill. Thought my throat was closing on me. It turned out I was just trying to avoid upchucking or something, so I had to cancel class. But hopefully this video will go a little better and I won't have that problem. I don't know what's wrong with me. I'm pretty sure it's Ebola. It's either Ebola or some hemorrhagic fever from some foreign country that I've never been to. I'm pretty confident. That's what my hypochondriasis tells me. So feel free to laugh at me. I enjoy laughing at myself. All right, well, we're supposed to be doing chapter 43. It doesn't seem like we have any more questions. So the problem with doing 43, I like doing it and I want to do it, but we really have to fit it at the end of 241 instead of 242, because at the end of 242, we fit in quantum mechanics, which is really 3 big chapters that need to be covered. So we don't have room to throw something else in there. So we put elementary particles in here just as another intro to modern physics. So y'all get basically special relativity, and you get elementary particle physics. Sometimes I'll do nuclear if I can fit that in. Sometimes I'll throw chapter 44 in, which is on the Big Bang and cosmology, which I find super interesting, and most students don't know much about, so I try to cover that. But it looks like we might do 43 and maybe 44 before the semester's over, because we still got this week and next week that's actually class time as opposed to exam time. So the problem is, though, that you haven't had quantum mechanics, and there's some things that we have to use from quantum mechanics, like the uncertainty principle and the de Broglie wavelength and stuff like that, that we have to use to actually study elementary particles. So I'll show you those problems and how they work, and they're just equations you're gonna have to add, and they're really not hard problems. It's E equals mc squared, we got that from relativity, and we got E squared is equal to p squared c squared plus m squared c to the 4th from relativity as well. And we know electron volts from relativity. So that's most of the stuff. And then there's just a couple things that we use, like the uncertainty principle and de Broglie wavelength. So I'll discuss that a little bit just to make sure y'all have enough background understanding to apply it without feeling like you're in danger or something. So what I want to talk about is basically historically how this happened. So as the late 1800s were finishing up, in the early 1900s, we had this sort of scenario going on where we thought we pretty much figured out all of physics. Most people say, well, with Maxwell's equations and with Newton's laws, of motion. We just have to apply those things as we've been taught and see that they're right, you know, maybe 7 decimal places instead of 4. And that's pretty much how they thought it was going on. But in that early 1900s, there was a couple problems going on. One was basically that when you heated up a metal object, it would radiate energy. And if you make a graph of that energy on the vertical axis versus what wavelength that energy is delivered it in on the horizontal axis, you get this curve that's really steep on one side and then reaches a peak and gradually falls down. That was what the problem that Max Planck studied and solved, but he had to make what we call a quantum hypothesis. Another thing was that there was the spectra that came from atoms and molecules. When you basically heated them up, they would actually produce radiation that if you spread, say with a prism or something, would actually have very distinct parts of the rainbow shown, but black everywhere else. And it would be a different set of lines for different elements. Like hydrogen looks significantly different than helium, which looks significantly different from lithium, which looks significantly different from water, and all this stuff. That was another problem to be solved. And there was the photoelectric effect, which was a problem to be solved. And all three of those resulted in basically the creation of quantum mechanics. So it was called the ultraviolet catastrophe, is what the problem that Planck solved was. And what he did was he said, okay, I've tried to work out this equation that fits this curve. And in fact, I get really close. And then I do part of this mathematical process that I try to do where I try to take this discrete variable, you know, one that goes from 1, but then it skips all the numbers between 1 and 2, and then it does 2 and skips all the numbers between 2 and 3 and does 3. You know, that's a discrete number. He had made a certain variable discrete like that. And then at the end of the day, you're supposed to, when you're finished that calculation, do a limiting process where it forces the number to become continuous. And he was getting really promising results until he did that last part. And that last part was the part that made it continuous. So he said, look, here's my publication. It appears that the energy of a photon of energy, which is a particle of light, basically, has to be some integer, 1, 2, 3, 4, 5, times some constant, which we named the Planck constant for obvious reasons, times the frequency of that color of that photon, basically. And that H times F became the quantum mechanical equation. The fact that it was discrete was amazing and told us something new about nature being not continuous. And that introduced us to the Planck constant, which is, it turns out to be experimentally a very, very small number. It's 6.63 times 10 to the negative 34th. So imagine a 0, a decimal point, 33 zeros, and then a 663, and the units are joule seconds. So that was what that gave us. Einstein tackled the photoelectric effect, and for it, he won the Nobel Prize. And that basically made use of the that same H bar omega that Planck had given us. And then Bohr comes with his model of the atom and explains that spectra stuff. Well, when all that's done, what we're starting to see is, okay, so we've got this weird reality in that it appears the thing that Newton treated as particles, in other words, when Newton worked out his optics, which he wrote basically all we really need to know for optics, except in most extreme cases, he did that all treating light as a particle, okay? After he died, Huygens and various other people found all the ways that light really was a wave, and in fact came up with the exact same expressions that Newton did, using electricity and magnetism and stuff like that. Maxwell did as well. So that there was a big problem. We had this scenario where light could be a particle, could be a wave, and ultimately what we decided was on the principle of complementarity, which basically is not like, hey, you look really nice in that shirt, but hey, you complete me, like in Jerry Maguire or something. So when they say complementary, they're meaning that the wave description of light and the particle description of light are both needed to fully understand light. And if you're doing a new experiment, you don't know which one it's going to behave as, a particle or a wave, until you actually do the experiment for the first time. And then if you change certain parameters about it, you could actually change it back again to a different form. So he saw evidently, or everybody saw evidently, that matter had this dual personality where, or excuse me, that light had this dual personality where it could act like matter, which is a wave, or excuse me, which is a particle, or it could act like light, which was a wave, right? So it was really a weird scenario. Well, de Broglie comes along and says, okay, well, I can't imagine a universe this beautiful, this amazing. And, when we talk about the elegant universe, for instance, in Brian Greene's book, that's sort of hitting on the idea that physics is beautiful, physics is elegant. And what it means is a high level of symmetry, and there's a lot of just beauty in the fact that it's understandable at all. There's no reason why we deserve to know how the universe works. It could be on completely random rules, but instead we find several handfuls of equations that can explain almost everything. So that's pretty beautiful by itself. And then you see these beautiful symmetries in equations, and you see these beautiful symmetries in nature. For instance, there was one time where they had basically a graph that looked like it had a dot, then it had a dot and another dot, and then it had only one dot. So it didn't have this dot here that seems natural, right? And from that alone, two physicists, one was Murray Gell-Mann and the other one was Richard Feynman, both concluded there's no way in nature that particle doesn't exist. And from it, they actually predicted the existence of a particle and predicted its properties. Someone went and looked, and sure enough, that particle did turn out to be a particle that existed. It was the omega minus particle. And, Gell-Mann, for instance, got part of a Nobel Prize for that. If I remember correctly, he did. I think he did. Anyways, but that's what we mean by physics being beautiful, is this symmetry that existed, dot, 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 dot. There's no way in heck nature's not going to make that other dot match so that it'd be perfectly symmetric. And sure enough, they went with that, and it's right. And we have no reason to believe that's the way it is, but it is. So far, it has been. So de Broglie does the same thing. He says, I cannot imagine a universe in which light has this particle characteristics, which is like matter, and wave characteristics, which is like what we expected as light, and matter don't have the same scenario. So he just basically said, well, I have no reason to believe that matter acts like a wave, but it's gonna. And he said, here, I'll use my dimensional analysis and figure out what the equation would be. And he wrote it as his PhD thesis. And his PhD advisors were, livid because they saw this guy who was actually really bright, but he came up with this bizarre idea that they just couldn't imagine. There's no way in heck atoms and particles that we've actually seen now. We know about the neutrons and the protons and electrons and stuff like that. There's no way we're going to find that those things are acting like waves. That's just insane. So the story has it that they kept changing his thesis defense date and not telling him, because the problem was de Broglie was doubly noble. He had two noble bloodlines from two different countries. And it's bad enough to offend one noble, but to offend two nobles could really get your university in some hot crap. So they did not want to grant him a PhD. Luckily, around this time, 1917 or so, Einstein was touring the world as a superstar that he was, because he basically predicted the way light would bend around the sun in his general theory of relativity. And he happened to be traveling in this area where de Broglie was studying. And he met with the professors there, and they said, hey, we have this really bright student. He's got us a bit in a pickle, but he's done something that we think is kind of crazy, but we thought maybe you might see something into it and be able to make use of it. And Einstein says, well, I'll check it out. And Einstein, that night, say over, before he went to bed, he read over the thesis and then came back next morning and says, it's one of the most incredible ideas I've seen in a long time. So they, of course, gave him his PhD. So he got his degree. And in fact, we now have this god-awful equation that says the momentum of a particle, P, is given by h over the wavelength. Or another way of looking at it is the wavelength of an electron, say, is given by h over the momentum of the electron. Okay, so that's the major things that you need from quantum mechanics to make sense of this. The other thing is the Heisenberg uncertainty principle, and I'll show you that as well. So let me flip to this. Actually, I'll wait a second. I'll flip and show you that equation once we get started, but I wanted to give you a little bit more history. So we had found the neutron, we had found the proton, we had found the electron, and we'd actually been interacting with the positron, which is the anti-electron, but we didn't necessarily know it. We just knew something funny was going on. We had photons as well, which turn out to be massless particles that are actually light, but they do something else that's kind of weird we'll learn about later. We knew the alpha particle, which turned out to be the nucleus of a helium atom, and that was about it. But by the 1930s, we started running into a buttload of particles. So we discovered that there are other particles like electrons, like the muon, for instance, but it was one that had like 207 times the mass of the electron. And then there were neutrinos. That was weird. And then later we were forced to conclude that not only are there neutrinos, but there must be 3 different types, because a certain experiment we did to tell whether or not we were right about how the sun worked suggested we should get 3 neutrinos a day from this experimental apparatus. And we dug a deep hole and we put basically a huge Olympic-sized swimming pool tank almost a mile under the surface of the ground. And we put the right chemicals in there to detect these neutrinos. And if we knew exactly what we were doing regarding the sun, then given where we are, how far away we are, how big the tank is, and how far away it is from the sun, we should get 3 neutrinos a day. And we got 1. And then the next day we got 1. And then the next day we got 1. And we're like, oh, this kind of stinks. We're pretty confident we knew exactly what was going on in the sun. So someone said, well, let's not do the hard work. Let's consider something simple. Maybe there's 3 types of neutrino that exist, and they can spontaneously flip back and forth into those other types. And that would explain the 1/3 of what we expected, which seems absurd and stupid and ad hoc and all that's ugly about, what people think about scientists. Are just going to throw, whatever at the wall until it hits something. But it turns out it's right. Lo and behold, we predicted the existence of 2 other types of neutrino. We predicted somewhat what their properties would be, and then we found them. And we found under what circumstances they're produced. And sure enough, we discovered that when we made a new device that was even more expensive and also way underground, we got exactly the number of neutrinos that we expected. And therefore, we did understand what was going on in the core of the sun. So that brought us into some more particles. We were like, oh, wow, this is kind of cool. And we ended up having basically elementary particles / fundamental particles. And your book is defining fundamental particles as the particles that have no internal structure. In other words, they're infinitesimally small, probably, because you can't say they have a certain radius or anything. And elementary particles are often used as the things that aren't made up of other objects, aren't made up of other particles. But I'll never ask you a question to discern between the 2 of them, because I never remember myself. I just look it up every time because it's not my area of physics. And I figure you could probably do the same thing too. So you might run into a question like which one's elementary and which one's fundamental, say in your homework or say in your practice test, but you're not going to find it on the final exam or on a test for me. I'm not going to ask that. Okay. So at the end of the day, what are these quote unquote elementary particles / fundamental particles? So to date, it seems like unlike the ancient Greeks, who thought the atom was the fundamental thing, the elementary part, if you take, say, a block of aluminum and you cut it in half, and then you take half of that and you cut that in half, you take half of that and cut it in half. That was the mental experiment that the ancient Greeks did. And they decided there's 1 or 2 choices. The one choice is you can do that forever and never run out of a half that you can cut in half. They just thought that was absurd. So the other choice came to be the one they chose. And that was that there's some point at which you can't divide it anymore. And the Greek word for divisible was tom. And the prefix for not is a. So atom is what they called this particle. Now, we've decided that that's not the smallest thing. For instance, if you take a compound like I don't know, iron oxide, which would be rust, basically. If you cut that down to the smallest thing that still behaves like rust, that actually is a molecule. So that's the smallest of that type of thing. Now, if you were able to, heat that up and break it apart into individual atoms, you'd get atoms again. But we've since discovered that the atoms are made of protons and neutrons, which are baryons, and they're in the nucleus. And there's even a baryon number that we use for everything that's in the nucleus. Is a baryon has a +1, and its antiparticle has a baryon number of -1. And anything that's not a baryon has no baryon number. So weird stuff like that. We discovered there was also these middle-sized particles, and they called them mesons, some of which turned out to be the leptons. And we decided there were, in fact, particles that acted to carry force. In other words, forget about forces and fields, which we've learned about with gravity. We imagine that gravity from our sun creates a field of affinity, if you will, that when a mass gets near it, it gets tugged based on how far away that mass is and how big that mass is. So the field is an equation that tells you the force at a given distance and what direction it points in. And then when you give it a number like the mass of the other particle, you just multiply that by that field part, and it'll give you the magnitude and direction of the force it feels. So that's the idea of force as a field and as a thing. Well, once quantum mechanics came on the scene, we felt a need to describe it in an otherwise fashion. And that otherwise fashion is imagining as if particles interact not by forces, but by exchanging particles. So for instance, like charges repel and unlike charges attract. So if you pictured two protons moving towards each other, they're both positively charged. So we're going to do like this. Well, that can be easily explained with a law just like Newton's law of gravity, but it's called Coulomb's law. And that can be repulsive or attractive, whereas gravity can only be attractive, as we know now. So when we send these two particles next to each other or towards each other like this, what we picture is going on is not that this one creates a field that causes this one to change its direction and path and applies a force to it, but rather maybe this one spontaneously creates a photon, and that photon shoots away from it. As it does, that causes this proton to change its direction a little bit, sort of like if you were riding maybe a small child. This gets a little dangerous here, but let's say a small child because their mass is light, or at least a petite person carrying a really big caliber gun on on ice skates. If you fire that gun, the fact that you're on ice skates is going to make you slide backwards in recoil. So that's the same thing happens if you fire off a photon this way, it's going to deviate that way. So that explains this one moving this way. But then it's also going to run into this one, and that's going to cause it to deviate that way. So you end up getting the same effect as if there was a force acting. So that became a force carrying particle. In fact, that is what the photon is in electricity and magnetism. And because the force, the electric force that we've studied, evidently can reach infinitely far away, it turns out that mass had to be zero in order for that to happen. So that's another type of particle, and we call them gauge bosons. So gauge bosons are the particles that mediate forces. They expect there to be one for gravity. We haven't found that. That would be called the graviton. The strong nuclear force was originally thought to be the pion, and Yukawa predicted that we'd find that particle that was responsible for this. So he was one of the leaders in discovering the idea of particles acting as forces instead of actually being forces. And he predicted roughly the size, and lo and behold, we found the pion was right in the ballpark of what he found. But we later discovered that those pions can be broken down further, and in fact, the force is a gluon. And then the weak nuclear force, which is another force, happens to be mediated by the W and the Z particle. So those are all gauge bosons: the gluon, the photon, the W and Z particles, and the graviton, if we ever find that. Okay, so there's four fundamental forces. Turns out the strongest one is the strong nuclear force, and about 100 times weaker than that is the electromagnetic force, and about 1,000,000 times weaker than that is the weak nuclear force, which uses the W and Z particles, and about 10 to the negative 38 times, is actually, I said 10 to the, about a millionth the strength of that. I mean 1,000,000th of the strength of the strong force. So the electromagnetic force is about 100 times weaker than the strong nuclear force. The weak nuclear force is about 1,000,000 times weaker than the strong nuclear force. And get this, the gravitational force is about 0.37 zeros and then a 1 times weaker than the strong nuclear force. So gravity really is really weak. Okay, that being said, it's one of our most important and most obvious forces. All right, so that's sort of the intro to what happened. And it was even, when we introduced quantum mechanics was made from conservation of energy. Dirac realized immediately that Schrodinger's equation, which is based on conservation of energy, was based on classical energy, and he didn't feel that was appropriate. Since we know about relativity now, we really need a relativistically correct one. And he made the Dirac equation, and people initially thought he was gone off his rocker, and they complained this can't be a real equation because it's got negative energies. And Dirac basically said, this equation's right because I worked it out and I know it has to be right. Therefore, there must exist antimatter. That's literally like as cocky as Dirac was. He basically said there's no way my equation can be wrong. And in fact, I suspect these negative energies are the energies of particles that have not yet come into existence. And in fact, if they come into existence, they will be antimatter. And in that sense, the vacuum is made of a bunch of particles and they're antiparticles instead of just nothingness. And lo and behold, guess what? He was right. Within 4 years, we discovered that we had found sometime before, we had seen it already, in other words, but we did discover we had found the positron, which is the antiparticle of the electron. Now it appears everything has an antiparticle, but some particles are what they call Majorana, M-A-J-O-R-A-N-N-A, I believe it might be one N, particles. And those are particles who are antiparticles of themselves. So that's what we're going through now, is we're going to try to make sense of all that. So I got to talk to you a little bit about this quantum stuff so we can know what's going on with that. And then we'll start into solving some problems. Anybody have any questions on that sort of history that I just gave you? It's a little jumbled. I went back and forth and stuff like that, just to make sure y'all didn't know anything that I was saying. Not really. I was, just flying by the excitement of the moment to explain to you all this stuff. So if you have any questions, I certainly understand. Nada. Okay. All right. So let me turn on my document cam. And the first thing I'm going to introduce is the Heisenberg uncertainty relationship. It turns out that Heisenberg worked out entirely different quantum mechanics in some sense than what Schrodinger did. Schrodinger came up with his Schrodinger equation. And when you take 242, I'll show you how one way I think he might have come up with it. But right now, I'm just going to tell you it's a conservation of energy thing. And he found out that if he pretended kinetic energy was this operator and let's say energy itself was this operator, then he could get an operator equation that acted on this wave function. Only it was weird because the Schrodinger equation came out to have an I in it, which is the square root of -1, an imaginary number. So that was a bit problematic. But in the end, he came out with a robust, easy to apply theory. Heisenberg really was brilliant. He basically derived a form of quantum mechanics using nothing but matrices, because he realized that when you're actually doing the process of measuring things, you're measuring things that would appear as elements in a matrix. And when you multiply the two elements, those are the things you can actually see. In other words, the things you can actually measure, and those are the only thing that were relevant. And it later was done by some brilliant mathematicians, not Teller, but I can't remember the guy's name now. I have his book right up here. I have one of his books right up here. Where's it at? It's one of those Hungarian guys, freaking brilliant. Oh, well, I can't find it now. But anyways, I'll probably remember it later. But he's one of the people that worked out that the two theories were exactly the same. But by the very nature of it being the type of equation that it was, Heisenberg said that it was obvious that this must be true. And it's basically that the uncertainty and the momentum in the x position multiplied by the uncertainty in the x position was greater than, and we often use two squiggly marks instead of greater than and equal to. Sometimes we use greater than and squiggly to h over 2 pi, which is defined to be h bar. So that's one of the quantum conditions that exist. And there's really no way around it. Basically, what it's saying is if you nail down the momentum really, really well, in other words, get it with very little uncertainty, then you'll know almost nothing about the position of the particle. That's the Heisenberg uncertainty process principle. There's another one. This is momentum and position. Notice it's x and x. If I do this for p sub x and y, I'll get 0 here. So it can be any, you can measure to any level of accuracy of px and y, or of py and x, or of pz and y, or p's, or let's say z and px. So all those different things are fine. It's just this one that doesn't. But there's also another one, and this is the one I'm going to be using, and that's the uncertainty in the energy times the uncertainty in the time is greater than or equal to h bar. Again, that's h over 2 pi. This is one we're going to make use of. So again, this is a weird oddity of quantum mechanics that we have to deal with. There's just no ifs, ands, or buts about it. You can measure this to say 99% accurate, but the closer you get to 100% accurate, the worse you know this one. And that's the same thing with this. So these will be used. Another principle from quantum mechanics was the one I told you about, de Broglie, where de Broglie said that the momentum, which we recognize as mass times velocity, is equal to h, Planck's constant, over lambda, the wavelength. And then the other thing I had told you about, which introduces h altogether, is that Planck had made the quantum hypothesis that E is equal to some n times h times frequency, where n would be 1, 2, 3, ... but nothing else. In other words, there are a whole number of differences between the energies that can possibly exist. 1hf, 2hf, 3hf, 4hf, 5hf, 6hf, all those exist, but nothing else other than them. Okay. Now it turned out this quantity, h, is equal to 6.63 times 10 to the negative 34th joule seconds. And that's actually what the Heisenberg constant is. And they do it in a lot of different units. You can do it in units of electron volts and nanometers and stuff like that as well. But the main thing is you need to know what it is, and you need to know that it's used in here. Okay. Now, what this is saying is, at least in a non-relativistic world where momentum is just mv, then momentum is equal to h over lambda. So you could say that lambda, the wavelength of a particle, is actually equal to h over p. Okay. And you can see that the units work out because this is joule seconds. Notice a joule second is equal to a joule times a second, and a joule is a Newton times a meter. So it'd be kilograms meters per second squared. That's a Newton times a meter times a second. And then momentum is mass times velocity. So that's kilograms times meters per second. And I think you can see what happens. This second cancels out with this second. And this makes kilogram meters per second. Okay. And this makes a kilogram meter per second divided by meters, basically. So because of that, because that gets rid of the other s, because of that, you end up getting just meters for the unit, which is the unit of wavelength. Okay. So here's the other part that you have to understand. If you want to study something and figure out, let's say, what the shape of an object is. So let's imagine a shape. And let's just say it's really, really small. Maybe it's an inch across, right? But it's shaped like this. Okay, let's say it's shaped like that, and it's in the middle of a 4 foot by 8 foot sheet of plywood laying on the ground. So you really can't look up there. All you can see that there's a little dark spot that's maybe an inch across from just about every direction I look. You can't see these jogs and hiccups in it and all that good stuff. So your idea might be to, okay, well, I'm going to take this big sheet of plywood that's sitting on it, and I'm going to shoot particles at it. And specifically, I'm going to shoot marbles at it. So I'll shoot a marble at this thing. And then I shoot it fast enough so I can see where it comes, so it can come back and, get rid, in other words, it will overcome its friction enough to get back to me. And maybe this one will bounce off right here. And you say, okay, well, I know the angle of incidence is the angle of reflection. So if I draw a bisector for this angle and then can imagine perpendicular to that, I can tell it landed somewhere right along this line. And combining that trajectory with this trajectory, you'd see it's right at this point, and that surface must be at that angle. And then you fire another one, say right here, and it comes off and does this. Again, the bisector is telling you it's pointing like this, and you're getting all that. But if you notice, this marble is so big, it's not going to go in this hole or this slot or this little thing at all. So you might say, okay, well, I've got the rough shape, and you'd say the shape right now looks to be like this, right? But you haven't gotten it right. You're missing some parts, clearly. So you say, okay, well, let's try some smaller stuff. So you start shooting individual BBs at it. And then the BBs can actually work out maybe some of this, and definitely can work out this little part and this little part.
And if you're diligent, it can probably work out that little part as well. But there's still some parts that you can't get, like that little hiccup there you can't get. So you try even smaller thing than a BB. You go and order some really specially made BBs that are even smaller. So what you realize is that in order for you to measure something of the size, say delta, then you need to use something of the size delta, right? So if we want to probe, say, the nucleus of an atom, which we normally picture as a ball of protons and neutrons like this, well, that thing is about 1.5 times 10 to the negative 15th meters across. And that means we need something about that big to do it. In other words, if we got smaller than that, that's great. But we're really, pushing the envelope trying to get something that small. That's literally a 0 followed by a decimal point, followed by 14 decimals, and a 1.5 after that in meters. So that's how you do it. Well, guess what? In order to get a really small wavelength, according to de Broglie, you have to have a really high momentum. Okay, so let's do an example of that. Let's say example 1. What is the wavelength of, let's say this is going to be a 2 GeV, let's say it's going to be a 2 GeV electron of a 2.0 GeV electron. Now, remember our rule from relativity was that if the kinetic energy was about as big or bigger than the rest energy, which for an electron would be E electron would be the mass of the electron times c squared, which we know is about 0.511 MeV per c squared for the mass. So that's that actual quantity. Okay, so we see this is much bigger, so that means we got to use relativity. And the equation that relates energy and momentum and therefore wavelength is E squared is equal to P squared C squared plus M squared C to the fourth. In other words, it's basically saying that the total energy squared is equal to the momentum squared times the speed of light squared plus the rest energy of the particle. Now, you're realizing that this energy is going to be on the order of 2 GeV, and it's when they tell you an energy of a particle, they really mean that this is the kinetic energy. Okay, so that's sort of this part. Even though it's written in terms of momentum, it's still the kinetic energy part. Since that part is 2.0 GeV, which is 10 to the 9th, and this is less than 1 10 to the 6th, you can see that the quantity right here is approximately equal to 0, which is nice because that means we're using relativity, but we don't even have to take into account the mass because it's not going to matter that much, right? So when I solve that for E, for P, I end up getting P is equal to E over C. Now I use de Broglie's equation and say that lambda for the electron is equal to H over P, and P is E over C. So I get HC over E is the actual wavelength. Just completely lost my words for a sec there. Now this energy is the total energy, but remember we were actually using it to solve for P. So we are actually using the P. It's just a matter of the P is E over C. So now I'll put this in, I'll say 6.63 times 10 to the negative 34th joules times second times 3.00 times 10 to the 8th meters per second. And then I divide that by, in this case, I'm going to say 2.0 times 10 to the 9th. That really got bad quickly. Times 10 to the 9th electron volts, and then I'm going to convert electron volts to joules by 1.602 times 10 to the negative 19th joules is equal to 1 electron volt. Okay, so notice that number down there converts this back to joules. So then I have a joule canceling out with a joule, and then a second canceling out with a second, and I get just meters. And when I put this in, I am going to get 620.8, and really these two are extra sig figs, times 10 to the negative 18th meters. And in fact, I can divide by 100 and multiply 100 simultaneously. And in so doing, I'll get 6.208, again, carrying two extra sig figs, times 10 to the negative 20, or excuse me, times 10 to the negative 17, excuse me, 16. Because 10 to the 2 times 10 to the negative 18th is 10 to the negative 16th. So that should be 10 to the negative 16th meters. That means you can actually probe to about, well, it's about half the size of the nucleus being about 1.5, this being about 6, so it's about maybe 4 times smaller, say, than the nucleus. So yeah, I can get really, really small details if I'm trying to use the electron to determine what a thing is shaped like. Now, again, this is the same issue that comes up with microscopes. So for instance, if you see a picture of an atom, an atom has the size about 10 to the negative 10th meters in diameter, roughly 10 to the negative 10th, something like that. Well, visible light only goes from about 350 nanometers to about 750 nanometers. So a nano is 10 to the negative 9th. So this is like 10 to the negative 7th. So you're not going to be able to see, quote unquote, an atom. You can't see an atom. What you can see is what an atom does to, say, electrons or other things that have a really small wavelength. And you can interpret that in the visible spectrum. And then you can see that, but that's all you can do. So that's why a microscope, has a limit to how well it can see. It can only see around the size of a micron, because this is 10 to the negative 9th. Move it 2 places to the left. That's 10 to the, that makes 10 to the negative 7 meters. So about 1/10 of a micron is all you can see with visible light. And you can't get around that. So we have to use other things. Any questions on that problem? So we are expecting you to continue knowing your stuff about relativity to continue this chapter. Now, the big question is, how do we go about making an electron go so fast? We're wanting relativistic speeds here. Well, a guy by the name of Lawrence at UC Berkeley came up with something called the cyclotron. And that's cyclotron. And his idea was this: basically, you working out the equations of electric and magnetic forces, he realized that a frequency of oscillation for something going in a circle would be independent of the speed. So in some sense, he could repeatedly flip a polarity of some voltage back and forth and force a particle to go into a circle such that it would speed up each time it went around the circle. So what he came up with was these Ds, and what they really are is a half circle and another half circle of the same radius, of course. But in fact, he sort of allowed a little bubbles thing to come out here. You could actually make it a little bit bigger if you wanted. And then when it came around here, it could just slip out and the particle is going to shoot off this way and hit a target. Okay, that was the cyclotron. These are supposed to be half circles. I know this one's way too bulbous, but the main point is this. So you drop a particle right dead in the center. And what you do is, if the particle, say, was an electron, then and you want it to go to the right, then you say, okay, well, I'm going to put a voltage on here that's positive, and I'll put a voltage on here that's negative. Well, that's going to cause it to accelerate this way, but you're also going to put a magnetic field in it. And this is a weird thing about electricity and magnetism, but magnetic fields actually cause things to move in weird directions with respect to the magnetic field. So I'll give you the idea of what it does, and I'll just tell you you're not really responsible for that, but you're going to know that you got to know the result. So for instance, let's see, I do this. This would go that way, so I want it. Okay, so I'm going to put the magnetic field sticking out of the page. This is like you're looking at the end of an arrow. So you see a circle with a dot in the middle. That's what this is representing, is a uniform, possibly very strong magnetic field. And the symbol we use for the magnetic field is B. Okay. So what's going to happen is, it turns out the magnitude of the force on a charged particle Q with a velocity V is actually Q times V crossed with B, the magnetic field. So you end up getting a force that's both perpendicular to the velocity and the magnetic field. So if this particle is going this way, it's a negative particle. So QV is actually going that way. And it turns out if QV is going that way and I stick my thumb in the direction of the magnetic field, then that tells me actually I should say QV is going this way, and I point my thumb in the direction of the magnetic field, my index finger, excuse me, then my thumb points in the direction of the force. What you're going to see is when it's going this way, it's going to actually cause it a force to go this way. And when it's going this way, the force is going to go this way. So eventually what happens is it goes in a circle. And then when it gets to this gap, that voltage switches to positive and negative. That speeds it up. So it goes in another circle. And then that speeds it up again down here, and then again up here. So it just keeps spiraling around and around and around and around and around and around until eventually it can make one last turn, shoot out here, and become hit a target. Okay. So Newton's second law, the summation of forces is equal to mass times acceleration. And the fact that this is going in a circle means that the acceleration is supposed to be v squared over r, where r is the radius of a given circle. Then that tells us that q times v times b, notice they're all perpendicular to each other in this scenario. So q times v times b is going to be equal to the mass of the electron, say. And actually, I'll do this in general, so I shouldn't subscript that electron, because you can do it with any particle. You won't, as long as it's charged. You couldn't do it with a neutron, because the neutrons don't respond to the electric force because they're neutral. But you can do it with a proton or a neutron or an alpha particle or whatever. So I'll just leave it as b as m. And then this would be v squared over r. You can see that one of these v's, of course, is going to cancel out. And now you can determine that the velocity is actually going to be q times b times r over m. That's the velocity of this particle at any radius r. So notice as the radius, radius gets bigger, the velocity gets bigger. The magnetic field stays the same, the mass stays the same. So now the velocity is bigger. So now the force is going to get bigger again, which again means that it can take a bigger circle given the strength of the magnetic field. And it's going to keep doing that and doing that and doing that. Well, what you need to know is really, how frequently do I have to switch this from positive to negative to positive to negative to positive to negative? Well, we're going to calculate the period for that reason. And the period would be the time required, let's say, to go from here all the way around to here. Okay, that's the period. So the period would basically be 2 pi times the radius, because that's the distance traveled, divided by the velocity, which would be q times b times r over m. You see the r's cancel out, and that's what Lawrence saw when he made this device. And with that, you get t is equal to 2 pi m over qb. And of course, frequency is 1 over the period. So in fact, the frequency should be qb over 2 pi m. And that's really the expression we need. However, all of these are useful. This, and this period formula. Okay. So that's called the cyclotron frequency. So what you do is you send to this thing that's making the voltage, you send a voltage source V as a function of time that looks like this. So, and you call this the positive one because that's what we're going to start it as. So what you'll see is at t equals 0, this will become positive, really, really large. And then it'll start to decrease and this side will flip to negative. But in half that time, the particle has now gone from basically here to here. So now it's polarized exactly the way we want it to be, and it'll come back around here. Then it's polarized exactly the way we want it to be again, and it'll come around here. So it works out really well. So let's look at an example. Let's say we have a cyclotron. So here's example 2. Cyclotron with R equal to 0.50 meters and T equal to 2.0 Tesla. What is the cyclotron frequency? I'll call that A. B, the velocity, and C, the kinetic energy of the electron. Okay. Well, we'll do the frequency first. We know that's QB over 2 pi m. So F is equal to Q, which is 1.602 times 10 to the negative 19th. Remember, we're using an electron. Okay, so 1.602 times 10 to the negative 19th coulombs is the actual charge. The magnetic field is 2.0 Tesla. The 2 pi is roughly 6.28 roughly. That's good enough, I guess, because I'm only doing 2 sig figs. And then, of course, the mass is 9.109 times 10 to the negative 31st kilograms. You haven't learned enough about electricity and magnetism necessarily to know that this Tesla cancels out with the kilogram down here and the coulomb up here to give you 1/seconds or the frequency of hertz. So I'll just let that slide, but just tell you it does work. So now I'm going to take 1.602 e to the negative 19 times 2. I'm going to divide that by parentheses 6.28 times 9.109 e to the negative 31st. And I get 56.01 times 10 to the 9th hertz. So that's pretty high frequency. That's actually in the gigahertz range. And I carry 2 extra sig figs again. So that's 56 gigahertz. Remember, radio, the highest frequency really is in the megahertz range, and that's on the FM scale. And the FM scale, I think, doesn't really go any higher than roughly what, 110, something like that. So 110 megahertz is 0.11 gigahertz, and this is actually 51 gigahertz. So it's, you know, or 56 gigahertz, which is, you know, basically 560 times further than that. So that's one of our answers. Any questions on that one? Now part B, what is the velocity? Well, the velocity is just QBR over M. And remember that R will be the final R. That's the radius of the cyclotron. So for part B, I'm going to say V equals 1.602 times 10 to the negative 19th. I'm going to leave the units off this time, just to spare room, I guess. 2.0 Tesla and 0.50 meters. All that divided by 9.109 times 10 to the negative 31. And that's kilograms. And all this should come out in meters per second. So I'm going to say 1.602 e to the negative 19 times 2 times 0.5. Obviously, they're going to cancel each other out. I'm going to divide that by, I didn't have to use parentheses, but I already did, 9.109 e to the negative 31. And in this case, I get 175.9 times 10 to the 9th, 2 extra sig figs again, and that's meters per second, which I think you can see is supposedly exceeding the speed of light. Obviously, that's not exactly right. And in fact, we shouldn't have been using maybe some of this because of maybe the MV is not right or whatever. But if you used a 2 Tesla battery, you could actually, in principle, get a speed that's actually bigger than the speed of light. And obviously, that's not relevant or real in physics. We've never had such a thing. We've hypothesized tachyons and stuff like that, but it just doesn't happen. Now, if you really want to just calculate the kinetic energy, you can see that this mass, or excuse me, this velocity being so much larger than the speed of light, clearly that means it's relativistic. And in fact, it should be, using K equals gamma minus 1 times C squared, but you can't even calculate gamma with that. So really, it's not an ideal problem. It's just some numbers I made up to see what would happen. And lo and behold, we've worked into a situation where we can't really even determine K except through methods of classical physics, which aren't correct. Okay, so if you wanted to do classical physics, I could square this, multiply it by the mass of the electron, multiply it by 1/2, and what I would get is, I'm going to take that and square it, times 9.109 e to the negative 31 times 0.5, and that's 14 times 10 to the negative 9th. So in this case, kinetic energy would be 14.1 times 10 to the negative 9th kilograms meters per second. So that is actually what the answer would be classically, but again, classically, it's not accurate. So I'll see. Okay, any questions on that? So sometimes that happens when you just make up numbers. They might actually violate the laws of physics. This is a case. In fact, if this was one of the homework problems and I was evaluating the homework system, I would have told them that this is an impossible value, which obviously is a lot easier to see after you do the problem than it is when you're just making up crap. But I've had stuff like that happen before. So any questions on that one? All right, now that is the cyclotron. And honestly, the cyclotron was the first accelerator, and you can see it gets you, normally if you use a more realistic size, 1 meter across. I think they made one that was approximately 1 meter across, but I would bet if they did make one a whole meter across, because they've got like old ones that have been made into the sort of sculptures outside of their physics department and various places on the campus at UC Berkeley. You can see photographs of them online if you want to look. But if they had that 1 whole meter one, that's what mine would be, that I just made up an example of, I would suspect they'd have a really hard time of getting a 2 Tesla field to permeate the whole thing. For starters, when you get a 2 Tesla field, it normally takes some superconduction, and superconduction normally occurs at liquid nitrogen temperatures. So that's a bit of a problem. And then getting one that's, basically in a vacuum, subject to sub-liquid nitrogen temperatures to keep the superconducting coils cold so that you can make a magnetic field that strong. It just probably would be unlikely. And in fact, I suspect they didn't have the technology to get a 2 Tesla field that big at that time. But the good news is this would have been something that they made. They used, probably government funds, National Science Foundation, stuff like that. They might even use some of the money from the Manhattan Project, stuff like that. And if someone like a politician would ask them, what purpose is this going to serve? How is this going to help an American in everyday life? Or how is this going to help secure our nation? against, foreign invasions from Germany or something. Because remember, this is roughly the 1950s, late 40s, that sort of thing. They would say nothing. It doesn't anything. In fact, your book gives a little bit of the actual testimony given before Congress by a scientist, and the scientist says, this thing doesn't really have any value except in the sense that America has value in, say, art and literature and poetry and stuff of that sort. That's the things that make our country in some sense great. And the only reason we can do that is because we're not a subsistence economy where you're just trying to make ends meet, putting food on the table, and don't have the relaxation time to make something beautiful and stuff like that. But in fact, in this case, it ultimately turned out, as it often does, it turned out that this is actually a very useful device. And in fact, we had a medical physics program in East Carolina where I did my master's and bachelor's degree, actually. That's why I was meshing two words. We had a medical physics program. And in fact, if you're a medical physicist, you can do dosimetry. You can also work on products. So you'd actually be the person that makes sure that piece of equipment's working properly. And there's other areas as well. But the big deal is they now use those to treat cancer. So if you have a particular type of tumor or something like that responds well to, say, proton therapy, which is this is a good case for a proton. In fact, if I used a proton there, it probably would have been better. I think it's because I used the electron that the speed got so high. If I used the proton, it would have definitely not gotten as high as violating the speed of light. But anyways, proton therapy, you've probably seen commercials for Hampton University lately on that. But the way that works is protons basically put out what they call a Bragg curve, an energy spectrum that looks like this. So you have the energies on the vertical axis and either space or even times on the horizontal axis. And you can adjust the energy of the beam to put this peak somewhere special. So what happens with the proton is the energy starts off high and then peaks and then falls off drastically. Whereas the electron sort of goes peak like this, and in actuality, it's sort of wider, a lot wider, and takes longer to build up and takes longer to settle back down. So if you have a tumor, say 3 inches below your belly button, and I don't even know if there's anything important there, I'm assuming that's probably where my colon or semicolon is. But anyways, if you shoot at that tumor from the front, then all the stuff for the first 3 or 4 inches is just, belly fat, skin, connective tissues, and pretty much no organs or anything that could really be harmed that much by the radiation, by the energy of the proton. But you can adjust the energy so that peak is right in the center of the tumor. And then what will happen is that'll come through there. It'll deliver heat to all the tissues before the tumor, and it'll deliver its most heat, its highest amount of energy right to the center of the tumor, and then it'll die off and not damage the structures behind it. That's an ideal scenario. Whereas if you did that with an electron, you're going to have to amp it up so high that it's going to have the peak right in the middle of the tumor. But there's so much radiation before and after that you're going to get damage on the front, which is mostly superficial and not that big a deal, but also way behind it. And that is a big deal. So that's why that's one of the reasons that proton therapy is markedly better than, for instance, electron therapy or even photons. Photons sort of are closer to like electrons in terms of that. But sometimes you just have to do what you got to do. And not only that, they try to limit the exposure. So like one day they'll shoot from this angle, and then the next day they'll shoot from this angle, and the next day they'll shoot from this angle, and the next day they'll shoot, all of it being centered on the tumor. So they're not damaging the same skin and tissues every time. And if it is going beyond the tumor a little bit, as it will, you're spreading that over a larger area, so it's less damage in each case. So that's another good thing. So that's a helpful thing. And these cyclotrons are actually the type of accelerator that can deliver that for certain energies, and it's really helpful. So not only that, we're now at a point, and we have been for I think almost 20 years now, where every type of cancer has been either put in remission or actually cured if found early enough. There's never been a type of cancer that we haven't been able to cure or put in remission. So yeah, these things are not that pleasant. They can be bad. They have side effects and stuff like that, but we're actually making some really good headway on treatment for cancer, specifically because of physics and a lot of stuff like that. To give you a perspective, I had a really good friend 30, maybe 20 years ago,
And then she was probably in her early 70s, late 60s, and she was one of the early survivors of breast cancer. And a really lovely lady, smart woman. She was like one of the first female CFOs or something for an international company. So she's really a brilliant lady, but she had breast cancer and she survived it. And because of the era she lived in, she literally would go to the hospital and lay against a big particle accelerator like the one we had at East Carolina. And she just lay against it for a long period of time, however long they told her. And she said she'd come home some days from treatment and she'd have black and blue blisters and burns all over her body because that was the only way they could get it. So stuff like this is making cancer treatments a lot more bearable. And it's all, partly because of elementary particle physics. So any questions on that? All right, so yeah, if you want to try that problem with a proton instead of electron, I remember now that's what I originally spec'd, but I didn't work it out, so that's why it happened. But if you want to work that out with a proton, that would be a good thing. And you see that the mass works out a little better, and the speed turns out to be a lot lower, so it's a little less unrealistic. Now they discovered that these accelerators, the cyclotrons, are useful, but they're limited in ability to speed up particles very much. And not only that, because they're going in circles. One of the fundamental things we learned from electrics and magnetism is that whenever a charged particle accelerates, and remember, acceleration can be speed up, it can be slow down, but it can also just be changing directions. And in this case, it's speeding up and changing directions. So when it does that, it radiates energy, and it's called synchrotron radiation. And in fact, you're losing energy. So as you're using the magnetic field and the positive voltage and the negative voltage to speed this electron up and up and up, the magnetic field actually can't speed it up at all. It just keeps it in a circle because the magnetic field causes a force perpendicular to the velocity, so it can't actually do any work that way. But in so doing, you're somewhat limited about how fast you can go and stuff like that, because the faster you go, the more radiation is radiated away and the less energy you get from it each time around. So they found other ways of doing it. One thing you can do is have a ring, a storage ring, where basically the particles going around, say, in the opposite direction, and then you can have them going in opposite directions and then wham, run them into each other. So you sort of get like twice as much energy as a cyclotron. Another thing you can do, once you start to get up high enough speeds, it's going to turn out that all of a sudden the momentum is going to be gamma times mv instead of just mv. And because of that, you're going to have a v-dependent frequency. So you can't have a cyclotron frequency anymore that's independent of R and V. You're going to actually have one that depends on V, and it'll have to actually get more frequent as time goes by. So they came up with a synchrocyclotron. So that's the next edition, is a round thing that has a frequency that can adjust based on the speed of the particle as it goes faster and faster. That allowed them to get bigger and bigger. But of course, it's still not the best thing because you're still wasting energy to synchrotron radiation. So one other way you can avoid that is you can still have to, if you're speeding it up, you're going to accelerate it, period. So that's definitely going to give some radiation, period. But if you speed it up in a straight line, at least you're only giving up the speeding up, the energy for speeding up, as opposed to the energy for speeding up and for changing directions. So they make linear accelerators like the SLAC, S-L-A-C, the Stanford Linear Accelerator. I don't know what the C is for. It might just be center or something like that. But they make accelerators like that. And in that case, what you see is initially these little tubes will be fairly small, and say the particle's right here, and the particle might be an electron. So to have a positive voltage tube right here, that attracts the electron to it. And then the electron goes through the tube, and then it gets about halfway through the tube, and the tube in front of that one is positive. And then as it gets out of that tube, this tube becomes negative, helping the electron go faster, as the positive is also helping it go faster through the next tube. And of course, you have to change the size of the tubes because they go different distances depending on how fast they are. And by doing that, you can string all those together and make a long linear accelerator. I think the largest ones in linear accelerator, I think, is they're getting ready to build one that's 3 miles, but right now it's about 1.7 kilometers is the Stanford Linear Accelerator. So that's another good one. Again, you can also make ones that go in huge circles. So that actually lessens the radiation per circle because the radius of curvature is a lot larger. They have, for instance, Fermilab has one that's
13 kilometers, I think, 12.7 kilometers, something like that. CERN has a really big one that's like 27 kilometers. That's the Large Hadron Collider. All these different particle accelerators, and you see cool pictures of them in your textbook. All these particle accelerators still work on the fundamental principle. Hey, a positive charge is attracted to a negative voltage, and therefore a negative charge, another way of looking at it. And a negative charge is attracted to a positive voltage or a positive charge, and you can compel it to do things like speed up by applying those electric fields. And you can apply magnetic fields to make them change their direction if you want, and that doesn't actually affect their speed, it just changes their direction. So putting all that together, you can get these really big accelerators, and it turns out the faster you go, obviously, not only the smaller the wavelength, that's super helpful, but also the more energy you can use, because it turns out when you go to, say hit a proton and see what it's made of, you're gonna have to take a proton and break it into its parts. And the total mass of the proton might in fact even be less than the total mass of the things that are added up to make it. Sometimes it's more, sometimes it's less, and I didn't look it up for the proton specifically, but sometimes you can have it such a way. But either way, you've got to have enough energy to not only hit the particle. So if you're ramming a positive particle into another positive particle, you got to overcome that Coulomb force, which is about 100th the strength of the strong nuclear force. And you've got to then get the strong nuclear force to kick in, and you've got to get the strong nuclear force to break apart and let those particles loose. And all that comes from, yes, more energy. So the higher the energy, the better off it'd be. And like I said, right now, it might be money that seems like we're throwing out the window because we're not getting any, immediate applications to it. But, 20 years from now, we might figure out, oh, wow, this is a really good hyperdrive for an engine that we could fly to another star system because their species is terminal otherwise, because the sun's going to burn out, right? So it could be all sorts of stuff. All right, so that's sort of where we go now, is basically to the various accelerators. I've showed you how the one basic one works, and I've mentioned to you the linear accelerator, how the tubes will get moderately longer. You can run accelerators back and forth against each other in opposite directions, so you can get even more energy. And what we might want to do is say, let's consider what is the kinetic energy and what is the, I don't know, how much energy does it take to accelerate a proton to like 90% of the speed of light or 99.9% of the speed of light? And then what is the kinetic energy in all those cases? So those are very typical types of problems you might solve when you're solving problems for particle physics. And we're going to do some of those. Another one is, if you have a certain energy accelerator, like the 1 tera electron volt accelerator, how much kinetic energy can a proton have from that, or excuse me, a photon have from that? So those are typical problems. Let me go ahead and turn on my document cam and give you some ideas on this, some examples to work with. So this will be example 3. This pen may or may not be dying. It's hard to tell. So what we're going to do is we're going to determine the energy required to accelerate a proton from rest to, so let's say, what energy is required to accelerate a proton from rest to V equals 0.99 C. So that'll be part A. Part B to 0.999 C. That'll be part B. And then what I want to figure out is what is the kinetic energy achieved at that speed. So let's say C, what is the kinetic energy at that speed? or at those speeds, I should say. Yeah, I definitely think this pin is dying. I brought out an extra just in case. So let me get that real quick. I'm gonna stick this over here. Okay, oh no, that's the wrong one. The blue one. There you go. Okay, so in this case, what we're going to do is we're going to try to basically figure out from the work energy principle how much of work must be put in to actually increase the speed from 0 to these various speeds. So what we're going to do is basically say, okay, well, work. This is part A. Actually, let me go ahead and do it in blue. Heck, this is a solution. I can make it a different color and it'll stand out a little better. Uh-oh, 5:45 to 7 o'clock already, isn't it? Crap. Okay, well, I will finish this problem in our next meeting, and I probably will finish the whole chapter in the next meeting. You'll see that basically there's some problems that you're going to do using baryon number, lepton number. We'll eventually get to strangeness as well. And with those numbers, there's certain conservation laws, and those conservation laws allow us, they're basically just things we made up to try to make sense out of the reactions we see with these itty bitty particles versus the ones we don't see. And what we do is if we never see a certain one, then we say there might be some kind of a conservation law. So we'll make up a series of numbers that all the ones that work lead to conservation of, but the ones that don't work lead to a violation of. So that's where we come up with these things like baryon number and lepton number. And in fact, lepton number has lepton electron number, lepton muon number, and lepton tau number. So there's a lot of different things. Of course, we still have our original stuff that we already knew about. Conservation of energy has to be abided by, but now it's conservation of mass energy. Conservation of momentum still has to be abided by, but also conservation of charge, which you hadn't heard of, but conservation of charge is a definite thing. And most of these things have charges on the order of basically the charge of an electron, 1 of that or 2 of that or 3 of that, until you get to quarks, and quarks have 1/2 of that or 1/3 of that. So we'll ultimately be able to classify all the different types of particles, but that's it. So you guys are free to go. I'll wait for the last person to leave before I split, because I'm allowing this time to answer questions. And y'all have a good day, and I will see you on Wednesday.
Have a good night.
You too. The whole time I was thinking y'all get out at 7:15. Should have sped up. Mario or Nate, y'all have any questions? Oh, Mario's gone.
Yes, sir.
Okay. You have a good one, sir.